Today, we are going to try and settle a really critical question and, move far beyond the
They
buzzword.
really are.
We're here to get to the essence of AI engineering. If you feel like you've been swimming in this sea of jargon AI, ML, DL, data science, and you just need a clear map, this is your mission control.
Absolutely. Our mission today is all about building the right mental architecture for you. We need to define the foundational concepts, sure, but uh, more importantly, we need to understand the true job of an AI engineer.
And the mindset.
And the core mindset, yes, that distinguishes success from, frankly, constant frustrating failure.
We're going to do this using a learning approach we call distill and build. It's a simple idea. We take these huge, complex ideas and we reduce them down to their cleanest, most essential forms.
That's the distillation part.
Exactly. And then we immediately reconstruct that understanding, layering in context and examples. Think of it as the shortcut to seeing the underlying patterns that, truly rule all these AI systems.
Okay, so let's start that distillation process right now by clarifying the hierarchy. If you visualize the entire field, you see these clear circles within circles. It immediately clarifies how everything is related.
Right. So the biggest ambition, the broadest frame, that's the outermost circle.
That is artificial intelligence, AI. It's the grand purpose, the big dream of making machines act intelligently, reasoning, problem-solving, adapting. AI is the destination we're all trying to reach.
And the main vehicle we're using to get to that destination, that's the next circle in.
Precisely. That's machine learning, or ML. ML is the method. So instead of programmers writing millions of explicit rules like, if the photo has whiskers and pointy ears, then it's a cat.
Which would take forever and never work perfectly.
Never. Instead, we give the algorithm a ton of data, a ton of cat photos, and it figures out the rules for itself. The whole shift is from hard-coded instructions to learning patterns from examples.
And then the engine that's powering this current explosion, especially with things like large language models, that's the very center, the innermost circle.
That's deep learning, or DL. And it's the modern engine because of its sheer sophistication. It uses neural networks with many, many layers. That's the deep part, which lets it extract really complex features automatically.
What do you mean by automatically?
Well, before deep learning, you had to manually engineer the features. You had to tell the system, hey, look for whiskers, look for eye shape. Now, with deep learning, the network learns those important features by itself. And that is just a massive leap in capability.
Okay, so we have the goal, that's AI.
Yeah.
We have the method, ML, and the modern engine, that's DL. But there's a fourth term we hear all the time, data science. Where does that fit in?
That's a great question because it's a source of a lot of confusion. Data science. It's a crucial function, but it sits alongside those building circles.
So it's not inside one of them.
No. Think of it this way. AI and ML engineering is focused on building durable, automated systems that learn and make predictions. Data science is focused on exploration, analysis, and generating insights.
Can you give us a practical example? What's the difference?
Sure. A data scientist might dig into sales data and find that, customers in one region prefer product B over product A. They then write a report. Their output is that insight.
Okay.
The AI engineer, on the other hand, might take that insight and build a system that automatically predicts which customers are likely to churn based on 50 different data points, and then deploy that system to run 24/7. That output is a scalable, live system.
That distinction is so key. Okay, so to distill this first part, AI is the destination, ML is the method we use to get there, deep learning is the high-powered engine, and data science is about providing the crucial understanding to make it all work.
You've nailed it. And now that we've distilled those concepts, we can build on that and define the actual job. Because if you're an AI engineer, you're told you build the model. But if that's only, say, 10% of the job, what's the other 90%?
I think this is the single most important clarification we can make today. AI engineering is, first and foremost, it's systems thinking.
Yeah.
It is not about training one model on a perfect data set and then just walking away.
Absolutely not. Training the model is the fun part. It's the visible part. The 90% is building the industrial assembly line around that model so it can actually survive in the real world. That means thinking about the entire pipeline.
We're talking about things like the flow of data coming in. Is it clean?
Is it labeled right?
Yeah.
Then you have the model training itself, evaluation, the deployment pipelines that let you roll out updates without, crashing the whole service.
And the parts people forget, monitoring and maintenance.
Critically, you have to handle versioning, knowing exactly which data, which code, which model config went into every single deployment. You need scaling, of course. But the hardest part, and where things fail silently, is managing the feedback loops and retraining.
Why is that feedback loop so difficult to manage?
Because systems can fail silently due to something called data drift. A normal piece of software, it either works or it crashes. It throws an error. An ML model can keep running perfectly from a technical standpoint.
But the world changes.
Exactly. User behavior shifts after a big economic event or a competitor launches something new. Suddenly, the model starts making bad predictions, but it never throws a technical error. The system needs constant monitoring and automated retraining to catch and fix those silent failures.
That makes perfect sense.
Yeah.
So the real job, the core takeaway, is building the whole infrastructure that keeps that learning system alive, reliable, and actually useful.
And to succeed at that, you need a very specific toolkit. It's a blend of 3 things that have to work in sync.
Systems thinking, intuition, and math. Let's start with systems thinking since we were just on that.
Right. Systems thinking is just stepping back and seeing the whole architecture. You can't just optimize one little piece. So what if you get a 2% accuracy gain in your model if putting it into production triples the server response time?
You've actually made the whole system worse.
You've made it worse. You have to anticipate those bottlenecks and dependencies across the entire flow data, training, serving, and monitoring.
Okay, then number 2, intuition. That sounds a little bit fuzzy, like something you're born with.
It sounds like it, but it's entirely a learned skill. Engineering intuition is just recognizing patterns instantly. It's that ability to just smell a mistake in a data plot or know instinctively that a certain step is going to introduce bias. It comes from experience.
From seeing thousands of pipelines fail.
Exactly. It's experience made instantaneous and predictive.
And the third piece of the toolkit is math. Now, for the learner who might be a little intimidated thinking they need a PhD, what level of math are we really talking about?
We're talking about just enough math, just enough to get the foundational mechanics. You do not need to be proving theorems. You need to understand the concepts.
Like what?
Well, understanding vectors as just directions and magnitudes helps you grasp how things are represented. Understanding probability helps you deal with uncertainty. And the big ones are optimization and gradients.
Let's focus on gradients for a second, because that's a concept that can trip people up. Could you distill that one for us?
I can try. Imagine you're on a mountain in a very thick fog, and you want to get to the lowest point in the valley. The valley floor is the point of lowest error for your model.
Okay, but I can't see it because of the fog.
Right. You can only feel the slope of the ground right under your feet. The gradient is simply that. It's the measure of the slope, which direction is steepest downhill at your exact location. Learning, fundamentally, is just taking a step in the direction of the negative gradient over and over until you can't go downhill anymore.
That is a great analogy. So the math isn't just abstract torture. It's the language of the system. It builds the mental structure you need to make your intuition sharper.
That's it, exactly. And once you have that toolkit, the final leap is the mindset. Before you write a single line of code, you need the right mental architecture. You need to recognize that everything, no matter how complex, reduces down to just a handful of recurring patterns.
Thinking in abstractions. These are the blueprints of AI engineering. And you say there are 4 key patterns that if you see them everywhere, you're operating at a much higher level.
Yes. The first and most fundamental is the learning loop. This is the core cycle. Predict, compare the prediction to the truth, compute the error, update the model. If you can't draw that on a napkin, you don't really get ML.
Simple enough. What's the second one?
The second is the data pipeline. That's all the prep work. Collect the data, clean it, transform it into something useful, train on it, evaluate the result. That's the sequence to turn raw stuff into actual knowledge.
And the third pattern is how you deliver value, which you call serving.
Right. This is how the model actually interacts with the world.
Right.
A user sends a request, you pre-process it, you run the model, you post-process the output, you send back a response, and you log everything. That whole chain has to be fast and solid.
And the fourth, which is sort of the meta pattern for keeping everything alive, is the improvement cycle.
That cycle is the heart of all engineering, not just AI. It's measure something, diagnose there's a problem, adjust it, measure it again. A great engineer is just constantly running that loop to make things better and more stable. Seeing all 4 of these cycles running at once is the mark of a mature engineer.
And that ties directly into this critical idea of clarity versus hacks. I think everyone, especially early on, falls for the hack.
Oh, absolutely. A hack feels so good in the moment. It's fast today, but it's slow forever because it's so fragile. Imagine you hard code some maximum value for a data feature, because one training example was a weird outlier.
It works on your laptop. You feel like a genius.
Exactly.
Right.
But the second that kind of outlier shows up again in the real world, the whole system breaks and you have no idea why.
Because it was a brittle, one-time fix.
Right. Clarity, on the other hand, might be a little slower today. You take the time to build a proper data transformation that handles outliers gracefully, but it is fast forever. Clarity means you understand the why. It's adaptable, it scales.
That why is the real speed. Knowing why a small data shift is wrecking your accuracy lets you fix a production system in minutes, not days.
And to maintain that clarity, you have to treat documentation differently, not like a user manual, but like an engineer's map. It needs active reading.
And you have a checklist for this, the 5 questions checklist for analyzing any new tool or library.
That's right. You start with 1, what problem does this actually solve? Forget the marketing. 2, what goes in? The inputs. 3, what comes out? The outputs. 4, what are the constraints? Latency, memory, data formats. And 5, the most important one. What do the minimal examples actually reveal about how it works underneath?
If you approach everything with those 5 questions, you build up the final assets. Reusable mental models. These are the deep structures that guide you when you're staring at a blank screen.
And we've distilled 4 that every AI engineer just has to have. The first is gradient flow, which we talked about.
Yeah.
Learning is always just a process of moving downhill.
The second is that constant push and pull. Bias versus variance.
This is just the simple versus complex trade-off. Think of a dartboard. High bias means your model is too simple. It consistently misses the bullseye in the same spot. It's underfeeding.
It's not complex enough to learn the real pattern.
Right. High variance means your model is too complex, it's overfitting, your darks are all over the board, it memorized the noise in your training data, so it does terribly on anything new. You're always trying to find that sweet spot in between.
Okay, the third mental model. Data as a distribution. This one sounds a bit more abstract.
But it's so practical. The model learns the shape of the data it was trained on. If the shape of the data in the real world changes, if that distribution shifts, your model will fail because its core assumptions are now broken. You have to be obsessed with the shape of your data.
And the fourth and final model, which is for operational health, is monitoring as an immune system.
Your deployed model is the body. Your logging and monitoring tools are its immune system. They're there to detect infections, latency spikes, prediction errors, those silent data shifts early, before the whole system gets sick. Those 4 mental models are your navigation tools for the other 90% of the job.
So we've taken this deep dive all the way from the basic definitions of AI and ML through the true nature of the job and into the kind of abstract thinking you need to master it. The 4 patterns, the mindset of clarity, and these 4 mental models.
The goal isn't just to memorize these facts. It's to, actually reconstruct your brain to see these patterns everywhere.
Right, in every complex system you look at.
If you really internalize these models, gradient flow, bias variance, data distribution, the improvement cycle, you will start to see them everywhere, way beyond just a neural network.
So here's a final provocative thought for you to take away. Think about that improvement cycle abstraction. Measure. Diagnose, adjust, measure again. Now think about a non-AI system in your own daily life. Maybe it's your team's weekly planning meeting or your personal sleep schedule or how you're trying to learn a new skill.
How could you apply those 4 engineering steps to diagnose its current problems and achieve a real, measurable improvement this week?
Think about applying systems thinking to your own life. Thank you for joining us for this deep dive.